In this series of videos, we are going to introduce the basic concepts and laws that we are going to use to analyze a circuit. The first one will be Ohm's law, and Ohm's law is defined for the simplest passive element, which we call the resistor. And then we are gonna, so the first one will be Ohm's law. Then we are going to talk about Kirchhoff. So this is spelled many differently in different textbooks. Okay. And then we're going to learn how to analyze basic circuit with this law. So analysis of basic circuit. Okay, so the simplest element that we are going to talk about is the resistor, and the resistor is the simplest element, which is across which the voltage and current are related by this algebraic equation. So we're going to start with the resistor. Okay, so in the resistor's level is represented by this symbol. Okay, and this resistor is a passive element, right? And the current through it, let's label the current I, and let's say the voltage across it, I call it VR or V of t at time t, and the value of this resistance is R. So the voltage and the current are related by this algebraic equation given by V of t, which is R I of t. So, well, because the resistance is constant, we could just write V equal to I, right? We could drop the t. Now, the unit of a resistor, right? So V is volt, and V is expressed in volt, I is expressed in amps, and R is expressed in ohms. So the symbol is V for voltage, the symbol is A for current, and the symbol is ohms for the resistor. Now, so we could also write this equation as given any two of this, right? We can always find the third one. So I can write this equation. This is equivalent to I equal to V over R. Now, so I equal to 1 over R times V. So 1 over R, right, is, so we did it by G, right, and that is the conductance, and it's expressed, right, and expressed is expressed in Siemens. The unit is S. So G, which is 1 over R, is expressed in Siemens. It's IE. Sorry, Siemens. And the unit is S. So I can add G here, which is 1 over R, and the unit is Siemens. And the unit is S. Okay, so given this resistance, and the inverse of that is G, right, which is the conductance. Now, so let's make sense of this equation. We know that V equal to Ri. So if I sketch this the IV characteristic, so I have I here and VI characteristic. So let's say that I have voltage here, or I have I here, and it doesn't matter. So let's say that I know the current and I wanted to calculate the voltage. Okay, so we know that V equal to Ri, so it's a linear equation with slope R, so I get like this, and the slope of this is R. Now, for now, we are going to deal with positive resistances, right? But later on, when we deal with dependent sources, right, the value of the resistance can be negative as well. So the equation or the sketch or the graph will be something like this. Okay. Now, so when we have this linear equation, then we can sketch the IV characteristic as this, or VI characteristic. Now, in real life, this is not going to be linear for all range. So you might have something like this. So something like sort of this. And so as you can see, the linear region is from here to here. Right? That's what we say is linear. Okay, for this linear range, right, where we could write V equal to Ri, or I equal to 1 over R times V, then we're operating in this range where this relationship is linear. Okay, so for this series of lectures, we are going to assume that we have this linear relationship, and we are going to continue with we're going to solve the network circuits, assuming that the resistance is linear, and then we're going to use that to solve the networks. Okay, so now when you have a resistor. So let's do an example. So what I'm saying is that when you have V, when you're given current, right, then you can, given the resistor, right, the resistance value, then you can find the voltage, given the voltage, right, and when you know the resistance value, then we can use that to calculate the current. Now, so when any two of these variables are given, then you'll be able to calculate the third one. Okay, so when I have a source here, right? So let's say that I have a source here, and the source is connected across this resistor. So let's say this is 10 ohms, and let's say this the current supplied by the source I is 2 amps, for example. Then the voltage, right, we can calculate the voltage V, which is, we know that is Ri, which is 10 times 2, which is 20 volt. Okay, all right, so and let's say you are given the voltage and the current. All right, so if we have this scenario where we have the source here and we know the voltage, let's say this is 10 volt and this is 5 amps, right? And then let's say we don't know the value of the resistor, right? We can calculate the resistor. So we know that V, right, the voltage across the resistor is I. So this implies that R is equal to V over I, which is 10 divided by 5, 10 volt divided by 5 amps, and this gives me 2 ohms. Okay, so R equal to 2 ohms. Okay, so given any of these three variables, any two of these three variables, then we should be able to calculate the third one, right, by manipulating this equation. Now, so now when we based off our previous videos where we define voltage and current, so when I have this scenario where I am given this voltage source, right, still let's say 10 volt, and we have I, and instead of giving the resistor, I will give you G. You're told that G equal to 2 Siemens. 2 Siemens. Okay, you're given the conductance. So that means we can find the resistor value, which is 1 over G, which is 0.5 ohms. And then we can use that to calculate. We, instead of just calculating the resistance value, right, we know that V, which is Ri by I, is G times V, right? So I is 1 over R times right, times V, right? So we can write a GV, so I equal to G times V. So Well, we know V and then we know G. So 2 times V, which is 10, does give me 20 amps. Okay, so just trying to show you how when you are given any two of this variables, then you should be able to calculate the third one. Now, so let's talk about the sign convention also. So let's say you have a source here. So let's say we flip the we level the voltage source is given as this. Okay, and you have this resistor. So, and we level the current going that way, I. Okay, so which is an arbitrary direction that we're given to the current, because in networks that you have, when you have many components, the direction of the current is not known until you calculate the value, and if it's negative, then the direction that you're given, the direction of the current will be that opposite. So for example, when I have 10 volt here, and let's say from that example that I gave above, when we have G equal to Siemens, so the current is level as you see there. So, and then for a resistor, we level the voltage, right? So when you have a resistor, all right, we have V and we have I. Okay, so this is V. All right, so then in this case, right, as you can see, V is negative Ri. Well, if like, I don't want to get you confused, but we could always write the Ohm's law, right, which is V, which is I, but then the voltage here, right, V equal to negative 10 volt, right, this element in parallel, so the voltage here will be negative 10 volt. So then we could write negative 10 equal to Ri. Okay, so that means we can find the current, right? So when we find the current I will be equal to negative 10 over R, and negative 10 times 2, which is negative 20 amps, right? So the current I is negative 20 amps. So the sign, right, the sign that you see here, right, indicate that the current is actually flowing in the opposite direction, right, in the opposite direction. Okay, so that means when we solve circuit, what we are going to do, we are going to level the direction for gonna give arbitrary direction for current, and then we're going to calculate the current, and then after we calculate the current, then if we have a negative sign in front of the value, then we know that the current is flowing actually in the opposite direction. Okay, so now we are going to stop right here. I don't want to make the videos too long. So what I'm going to do, I'm going to record another video. So I'm going to make a series where I'm going to start solving network that are more complicated. But before that, I'm going to introduce next, right? So next, and so we are going to introduce next, right, will be the Kirchhoff laws, right? So we're going to introduce the current law, Kirchhoff current law, and Kirchhoff voltage law. So please follow me for the next video. Thank you. Now to continue with this passive element, which is the basic one, which is the resistor. We are going to talk about the power, right? So electric power. Okay, so for resistors, so resistors are passive components, right? And they can only absorb energy, right? So resistors are passive component, and they can only absorb energy, can only absorb energy. Okay, so so let's define the power. So we know that, so let's say that I have this scenario, okay, and I have this component, okay, and the voltage across that component, right, is labeled as V, and so, and then the current is flowing this way, right? So I wanted to make sure that I level the direction of the current here. So now the power P, right, is defined as V times I. Now, so when we have a resistor, the current is flowing and top to bottom or top down, as you see on the last level here, and V. So because the current is flowing from plus to minus, right, then the power P is IV, where we account for the fact that the current is flowing from plus to minus. Now, when you have, so I'm giving this like in general, right? So, and then we apply that for the resistor. So let's say that we have this scenario where we'll still have the polarity of the voltage level as such, but then the direction of the current is this. So that means the current is flowing into this component from the negative polarity. So in this case, right, we are going to have P, right, for this particular case will be negative I times V, negative IV, right? So let me use a different color for the sign. So negative IV, right? And then here we have plus. Okay, so the sign here, right, is just a passive component. Passive sign convention, right? So this is called the passive sign convention, right? Passive, okay, sign convention. Okay, so now let me copy this down here. So copy, I'm gonna paste it here. Move it up a little. Okay, so and then let's say that I have this scenario, okay, where I have the polarity of the voltage flipped, but then the current is still flowing that way, right? So here P is also equal to negative IV, negative IV. This is just a convention, right? But that doesn't mean that the power is negative yet, right? So we're gonna have to calculate and see actually have the value of P, and then we are going to define whether the power is being supplied or the power is being absorbed. But for resistor, right, resistors are passive components that they can only absorb power, right? So, and when I have this scenario, okay, so the voltage polarity remain the same, but the current, right, is level going that way. Okay, so P is equal to plus IV. Why? Because a charge cannot be the charge that flows into this component are the same charges that are flowing out. So that means the current I is going into the device, and that the same current is coming out of that device V. Okay, so because we cannot create nor destroy a charge, right? We can move them around. So this is a passive sign convention, and then now we are going to use that passive sign convention, for the resistor. Okay, so now for a purely resistive element, which is the resistor, right? So we have I going that way, and V. So P, as you can see, because the current is flowing from plus to minus, is IV. But if you have the scenario where the current is still flowing that way, but the polarity of the voltage is given as such, so P here, right, is negative I times V. But what is Ohm's law? Right, V equal to Ri, because the current is flowing from minus to plus, is negative Ri. Okay, so for this case, right, V equal to Ri, because the current is flowing from plus to minus. But for this one, the voltage is negative Ri. So when I substitute that in this equation, I have minus I, which is negative I, which is I squared. Okay, so I like to emphasize on this. So when you have a resistor and the current is flowing, right? So the passive sign convention, Ohm's law here, V equal to Ri. But then if I have the scenario where the polarity of the voltage is level as what you see in the screen, on the screen right there, so then the Ohm's law will be negative Ri. Okay, so we are gonna have to calculate these values, right? And to then we see, because the direction of the current may be arbitrary, and all the polarity of the voltage is level arbitrarily. Okay, so then we have to calculate these values, right, to be able to tell the direction of the current. Okay, so then to recap, in both cases, when you have a resistor, okay, so when you have a resistor, so for this case, P, which is IV, right, which is I, so I times Ri, the voltage is Ri, so that gives me I squared. Okay, we can express it in terms of voltage. So when I write this equation, I know P equal to, so this is one of the equations for power. So we know that P equal to IV, that's the relationship we start with. So then we can solve for I, which is V over R times V, right? So which is V squared over R. That's the second equation. Now for this second case, we have P equal to I minus IV, because the current is flowing from minus to plus, minus I times V. And here also we have negative, right, I, and the voltage is negative I, so I square. So for this we have I square. But if you express it in terms of voltage, we have P, which is still negative IV, and so replace I in that equation, which is negative V. So it's negative. All right, so negative V times negative V over R, which is the current. It gives me V squared over R. So the power here is P equal to V squared over R. So as you can see, the equation for the voltage and current, we can use those to calculate the power absorbed by this component. This is just a passive, passive resistive element, or which is purely resistive, the resistor. So we know that P, which is I squared. So we can manipulate this equation to find I. So I will square will be P over R. So I is a square root of a P over R. Right? So we can always find the third variable given if we are able to calculate the other one, and then we can also calculate the given this equation P, which is V squared over R. This implies that V squared equal the power times the resistor. So V is a square root of P times R, so Rp, if you like. Okay, so we have, we can manipulate these equations as we like when depending on the variable that are given to us. Okay. So let's do an example. So let's say that we are given. Okay, so example. Okay, so find the power or the energy absorbed by the 3 kilo ohm resistor. So in the circuit below. Okay, so let's say that we have 12 volt that is applied to this 3 kilo ohms resistor, and we wanted to find the power. So we know that or if you like, let me just put power here. Okay, so the underlying energy absorbed, right? So now, so we can find the power, right? So we know that P equal to what? P equal to V squared over R. We know the voltage across that resistor, right, which is 12 volt. So that gives me 12 square divided by the 3 kilo ohms. Okay, so right, if you like, it's like 12 square divided by 3000 ohms, right? So now we can find this in milliwatt, right? So we have 12 times 12 over 3, right? 3k, right? So what is 12 divided by 3, which is 4, right? 4 times 12 is 48, right? So 48 milliwatt, that's P. Okay, so because we know the voltage, and then we know the value of the resistor, we don't need to calculate the current. But if we did, we can find the current I. So I, which is V over R, right, which is 12 divided by 3, 12 volt divided by 3k, which is 4 milliamps. So then P, which is IV, and the passive sign convention, the current is flowing from plus to minus. So I, which is 4 milliamps, times the voltage, 12 volt. So as you can see, 12 times 4, which is 48 milliwatts still. So whether you calculate the power, whether you calculate the current before calculating the power, right, you're gonna end up with the the same result. Now, so let's say that so we're going to do a few more examples, when we have more complicated circuit. So I have introduced the concept, and we are going to do more examples in the next video.